mainly medical image processing, but before we start, which Bishesh and Taman is going to present, I will briefly talk about learning on point sets. So, you know, we have been talking about learning, deep learning, and language, natural language processing, and there are many domains where you can use deep learning, like many kinds of data where you can use deep learning, and data modality and how data is organized plays a crucial role what kind of methods you apply. For example, when we're doing learning on sentences which has, you know, particular sequence of words or organized as sequence of vectors, or then you would use something like RNN or LSTMs. So similarly, when you learn on images, which is basically a ordered matrix, ordered a set of numbers, matrices, then you apply convolutions, right? So, yes. Okay. Is it turned off? No? Okay, I think I cannot operate that. Cool. Continue. Everyone, please. So now we're talking about not image data where you have specific order of points, pixels are arranged in specific orders, right? So we're talking about point sets. So can you see why it is different? When you have a set, let's say a set of vectors or set of anything, a set of objects, the sets, they are not arranged in a specific order. The order doesn't matter, right? So, for example, one specific example of set could be a 3D point cloud, where you have a bunch of points, let's say n number of points, where each point is represented by a vector x, y, z. And these points, you can put the first point as when you arrange it as a matrix, in the last row or last column or last point in the first column, it doesn't matter. When you render it, it's still gonna be the same point cloud. So this actually introduces a very particularly difficult problem, because you want to be invariant to order of these points. When you apply convolutions, this is not invariant to order of the pixels. In fact, that's an advantage, because now we could learn like the relative, you know, how pixels are arranged relatively to each other. We used that as a prior to learn on images. So in point clouds or any other point sets, you don't have specific order, like in the image where you have first pixel, second pixel arranged in row and columns. So that's the point. And there are many kinds of point sets. I'm giving an example of 3D point cloud, but there could be many examples of point sets. For example, if you try to learn on data coming from, let's say, financial data or a data of a user. Let's say you have 100 clients, and each client you give a feature vector. A vector, for example, could be age, how much they are spending in each month, or what's their earning. This kind of data. Each component would have an order in a vector, but the clients themselves, they would not have an order. You have to be invariant to the order of the data there. So that's the point we're going to make here. So for example, 3D points, let's say you have, in the point cloud in the left example, I'm just taking like 2 points, let's say. First point is x, y, z is -1 to 9, and the color intensity is 120, and the second point is 2, 3, minus 5, and the color intensity is 240. So you could arrange the first in the second and the second in the first and plot it. They would still be the same. So that's how it is. Here the order doesn't matter because once you plot them, they're still the same point cloud. So how are we going to learn on this kind of data? And in fact, this is quite common in real examples, that you have data which have this kind of nature. So we will focus on, for example, first we'll talk about convolution and how convolution is order dependent. And let's just try this example. I did not work it out myself, but let's try it now. And you can see that if you change the order of these vectors, you will get a different result that you cannot, once you get the result, you cannot recover the original result by changing order here. So that's why it's not order invariant. So if you do this example, and if you do this next example, for example, on 5, you will get different results, right? So let's do this example on this one. What will be the answer? So you have to do -1 times 1 plus 0 gone, 1 times 5, 4 times -2, 2 times 1, -1 times 3. You know how convolutions work, right? It's pretty easy. You just put it here and take it there and multiply and then sum. Minus 401? 409. 4 by 9. Oh, okay. So minus 4 by 9 here, right? So let's write it down. So let's go to the next, where I just swapped the third column with the fourth column. So the vector on the second column is still the same. I did not even change the order on the second column. Now I swapped with the third and fourth. Now will the results be the same? It won't be the same, right? What will be can you try it out? Just take it and apply it on this one, not on the fourth one, right? So -1 times 1 plus 1 times 1 minus 10 by 9. I guess he verified his results, right? Maybe. Maybe it's not correct. Minus 6 by 9. 6 by 9. So it was not correct. So yeah, 1 by 3, or 2 by 3. So it's 2 by 3, okay. So here's the problem. you clearly see there is a problem. If you apply convolutional nets, conv-nets on data which you want to learn as order invariant, then you will not get this, representation that is fit for your data. So how do you solve this problem? So the answer is pretty simple. You just do one-by-one convolution, right? I mean, when I first saw one-by-one convolutions, I was like, what? What is it doing? Why would you do that? Like, you just multiply by one number, right? Why would you do that? But why is that comes later? But check that it is order invariant, right? It should be order invariant of the columns. If you change the columns, you can get back the original by just changing the columns and the results. Again, it's just scaling the whole thing by 2. Yeah, I'll come to that. Yeah, it is still, you see that the what do you call this, width or depth? Depth. Channel, yeah, sorry. Yeah, I always get confused. The depth is still 1, so it is just scaling for now, right? So if you, by the way, if you're interested in this kind of data learning, there's also one nice lecture by Andrew Ng. Andrew Ng has a nice lecture on one-by-one convolutions and what it means to do one-by-one convolutions. In fact, I made this example somewhat inspired from that lecture. So it is order invariant, but it's not really learning anything. It's just scaling things, and it's just presenting the same thing, right? So, but in fact, you have to note that when you do deep learning, you have a number of filters and you have a number of feature maps. So feature maps, each feature maps comes from one filter. So let's say you had F1 number of filters before when you did convolutions. Then in the output, you would get F1 feature maps. And this is the dimension of your input. It's the same, right? So this size is the matrix size we're talking about before, like this size. But you apply a number of filters, not just 2, like 2, 3, 5, like many number of filters. Then you would have F1 number of feature maps at each location. So what does a one-by-one convolution do? In fact, if you have now, let's say you apply one-by-one convolutions now with with F number of filters for the input of size 1 by 1 by F1. So for each point you have F1 number of, so it's like a vector. You have each point is a F1 vector. Then you would get something like your size in the output will be F, and this size remains the same. So what it does is it changes the dimension of your input when you apply to one-by-one convolutions. So that's the whole point. You want to change dimensions, you want to go higher dimension, you want to go lower dimensions, and look for representation. When we did PCA before, we're looking for representation in a lower dimension. Like, it's all about representation, finding the correct representation to classify or to regress or to whatever. And here the point is you want to change the one-by-one convolution will change the dimension of your input to the output. So for example, if you had only all the F filters were 1, then it would just average out. It would just be an averaging operation. But the F filters need not be the same, right? They will have, each filter will have individual weight. And this is exactly what is multilinear perceptron. When you're doing perceptrons, it was a linear operation, right? On the input, you multiply vector by another weight vector. So this F vector is a weight vector now. But in deep learning, we have we introduced nonlinearity. For example, this after you apply the filters, you always apply some nonlinearity, like ReLUs. You throw away all the negative values and put 0 there. So these kind of operations will learn a higher dimensional. If you go to a higher dimension, it will learn a higher dimensional representation just by doing 1-by-1 conv. And then there is max pooling. Sorry, this is not. It's kind of misleading. So here until here we are good, right? So when we apply, we have F number of feature maps now, and you do max pooling. Let's say you have n by. So I guess I need to do it on the board. Sorry about that. So max pooling is just you max on certain dimension. So it could be first dimension, second dimension, third dimension. But in this case, you usually max pool on the dimension of the number of vectors, a number of features or data points. Let's say you have n data points, you max pool. And so you max on the, now you only have one data point feature vector. So it's a representation of all your data points. So for example, if you have n times 3 times feature maps F, now you will have 3 by F. I will write it down here, so you have it on the slides as well later. So that kind of operation will learn something that represents your whole set of data. All your data will be represented by some learned features. So that's the idea, and this is the paper in 2017, which use exactly these things to learn on point sets. So in this case, it is mainly 3D. It was learning on 3D points, but it could be any kind of points. For example, you have, let's say, is somewhere here from Ansel, or like if you had, a user who you could create a log of the user and use that as a feature vector and learn on, what the user is doing or what the is he going to buy new? You could predict, is he going to buy new packs, like data packs, or is he going to buy change the phone to another operator, or something like that, right? I also use this thing for learning on point correspondences, not on point 3D points, but 2D point correspondences. So it could be any number of things. So this is the architecture. So it's a bit, a bit too big to look at the same time. So we'll go through one by one. So the main operations here are you do 1-by-1 convolutions, you change the dimension, so you learn the representation in different dimensions, Then you do ReLU. So ReLU will introduce some nonlinearity that you will be able to. So it's not just perceptron now. Once you do ReLU, then you do max pooling. Now this will make a common representation of all your data. So you see that all these operations are invariant to order. This is the main point. When you do max pool of n-dimensional vector, the result will be the same no matter where each component is. It's still max, right? It doesn't matter what the order is. And the same is ReLU. So inputs is a set of vectors. That's what we want to learn on. And examples could be point clouds, mesh, or corresponding points in images, or other any kind of user data, or these kind of things. For example, if it's point cloud, you might have n cross 3, and the length of the number of the points, and 3 the dimension of the point, which is x, y, z, and such. So we have to represent, although point sets are not matrices, they are sets. We have to represent it as a matrix to learn on in a deep learning framework. So we arrange this in this kind of matrix, right? So 3 and then n. So it's 3 by n, right? Why did I write n by 3? So anyway, this is 3 by n. So we go to the. We need to do some pre-processing before we feed the data, because there are still some things that we don't want the network to be variant to. For example, you might have, take example of point clouds. You might have point clouds in different scales. You might have house represented in meters or house represented in centimeters, and that changes the scale. But what we want is we want to learn in making the scale not relevant. And also translation. For example, the point cloud could be far away or at the origin or wherever. So what we want to do is we want to center them first, center the sets first, and fix the scale, and then we go for learning. For example, centering is just you subtract by the mean, right? Scaling you can do in a number of ways. You can make the variance constant, like variance of the data to be 1. You can make the norm of the data, the maximum norm of the data to be 1, and the rest norm will be less than 1. Or you could, here I'm saying that the mean norm of the vectors should be 1. So there's a number of, so here xi could be any of the x's from 1 to n. So, for each of the xi's, we do this operation to fix a scale and to center. So the next thing is, for point clouds, you might want to rotate the points and to a particular configuration, because we have one more thing that could be that we don't want our network to be variant to for 3D point cloud. For example, this and this are the same point cloud. We want whatever we learn on this should also give the same results on this point cloud, although they are rotated. If we want to segment the point cloud, if we want to classify the point cloud, we want them to be invariant to rotation. So what we want to do is, whatever rotation the input point cloud is on, we take it to a particular canonical configuration. And that way we will be rotation invariance. But you have to be careful here, because depending on your problem, you might not want your data to be, your method to be rotation invariant. For example, if I wanted to compute rotation of this, if I wanted to regress on the rotation, then I would not want this to be rotation invariant, because I want to get the rotation as output. So you have to be careful whether you want your method to be rotation invariant or not. So this is in the big network. The first part is you transform your input to a canonical rotation. So it doesn't change the scale. It doesn't change the structure of the point cloud or your data. It just rotates to a particular configuration. And the weights of the rotation depends on you learn them by combining the input, right? Your rotation depends on the input. That the weights and all these, the layer will be learned during the training procedure. The next thing is you want to do a higher dimensional embedding of your, on each, you have 64 filters, then it will give you 64 feature maps, so n by 64. And then feature transform is basically the same thing as rotation before. We again want to rotate in a particular configuration. And then again, we want to do a number of these one-by-one convolutions. How many depends on how complex your data is and how many data you have. For example, if you have a lot of data, you might be willing to do more, build more complex networks or deeper networks with lots of filters. If you don't have enough data, then it's not worth it, right? So in the end, we go to a very high dimension, 1020, n by 1024. Like each point is represented by a 1024 vector. So this is a change in dimensionality. Then we do max pool. So max pool is again, it's a permutation invariant operation. So it will summarize all these points, all these n points vectors into one, global feature. That will summarize the points. Finally, you have a global feature vector. Now it depends on what task you want. If you want to classify each point cloud or each set of data as something, then that's enough. But maybe you want to classify each point in the data. Then you would have to combine these n by 1024 feature with 1024 feature global feature. So both local and global. Then you would be able to, for example, segment the point cloud or find parts in the point cloud which are relevant, or for example in data, other kind of data as well. So this is the end of the point set learning on point sets, but there is something I wanted to talk about, the other part of 3D vision, which will be relevant in also pixel locations in two images. The same between the same point projected in two images. What would be the relation? And that was the fundamental matrix, right? So sometimes this relation, we cannot use it to transfer one point of the image to the other point because it's rank 2. So what we will do is, if you try to transfer it, you will get a line. If you transfer the point from one image to the other using the fundamental matrix, you get a line because it's only rank 2. So there are some rank 3 relations, like full rank relations between images, pixel locations in images. And in fact, it has a very nice application How many of you use your phone to get panoramas? Like, I guess many people, right? You do like this. I guess you also do panorama selfie, or I don't know if that's possible. So, in order to make a panorama, we will see later that what you need to do is, if you have two images, you need to transfer each pixel here to this reference image, or the other way around, whichever. And then you add information that is not present in that image from here. So you're just extending the images, the first image, along using the information from the other images. So it goes something like this. Let's say you have a pixel location Q1, and you have another image which has pixel location Q2. These are corresponding points. Then they represent the same pixel, the same information. What you do is you try to compute a relation H that will transfer Q2 to Q1. Then it will take the pixel intensity as well, right? So the part highlighted in blue are common in both images. Of course, if you take two images, it will of the same part, same object. Some of this will have common parts, and you will also get some parts which are not common in these images. So the gray is the part that is not common. And image stitching or panorama, creating a panorama image means you will transfer this gray part to this side, right? So this gray part here, that's what you want to do. And you want to find a relation H between each pixel in the image. So it turns out that I will directly go into the results and not the derivation, but it's pretty simple to prove it. You can try it at home. If your camera is rotating like this about the camera center, what you will get is that you can have a single H, a 3x3 matrix. In fact, for a calibrated camera, where you have UV1, not U prime, V prime 1, this is simply the rotation. H is simply the rotation. So you can just get the pixel locations of the other corresponding point by transforming using a 3x3 matrix. So this is a very strong result that means that you just need to get one H, and that will transfer every point from here to here. So this is a linear relation, right? Except that H, Q1 and Q2 are expressed in homogeneous coordinates. So when you have these homogeneous coordinates, this becomes a projective relation, because then in the end, to get the result, you have to again divide by the last component. That's why there's a division operation, and it's not linear. So what you do is you form these equations. Now if you have 4 points like this, if you identify 4 corresponding points, you will have, from each equation, you will have 2 independent equations, because Q1 is UV. So each component of this vector and this vector has to be the same, right? So you get 2 equations from here, and if you have 4 points, you'll get 8 equations. And then you do solve as we normally do in linear algebra. This will give you H. Then you just transfer this point using this H here, along with the pixel value or pixel intensity. Then you have stitched 2 images into one. So this kind of registration, this is called homography. So here you have 3 by 3 matrix, and the scale is again irrelevant because it's a homogeneous coordinate system. That's why it has 8 degrees of freedom. You need 8 equations to solve this. So I think Vishesh is going to talk about other kinds of transformations that you have in images or especially in medical images. And we will carry on with the course. So one quiz in the end. We talked about optimization some days ago. So I was just wondering, can you tell me what condition stochastic gradient descent will act like gradient descent? You already studied this. What did you say? What is the answer? Small? Sorry. Small data size. Yes, okay. That could be, that's also true. Small data size, for example, if your data is only one size, then it's the same, right? It's exactly the same. But if you turn into your optimization, gradient descent or stochastic gradient descent, there's another hyperparameter. Yeah, there's a step size, right? So what does step size mean? So for each data in a stochastic gradient, your step size will change the input parameters according to one of the data. So if your step size were approaching 0, what would happen? And when you do one round of what you call one epoch, when you do one epoch, which means you go through all your data once, then your step size is practically 0. Then it's like you're doing one round of gradient descent, right? One epoch of stochastic gradient descent will be like one round of one iteration of gradient descent, because your step size is, let's say it's 0. So you have to visualize this thing, and this step size and all the learning rates and all these things the hyperparameters, they come directly from optimization. And when you try to tune this, you have to think about what's happening in the optimization. Why is it happening in something like that? So on to the next round. Who is it going to be? Taman? Thanks.